Hello everyone, how are you? This is Kevin Chen. It is my pleasure to present our Directvisor in VE 2020. This work is the collaboration between my lab in the Binghamton University and Industrial Technology Research Institute in Taiwan. Conventional multi-tenant cloud services enable customers to run traditional system virtual machines to scale up their IT operations to the cloud. However, the hypervisors used for virtualizing these platforms suffer from both performance overheads and isolation concerns. To address this concern, cloud operators have begun offering bare metal cloud service, which allows customers to rent dedicated remote physical machines. Bare metal cloud customers are assured stronger isolation than multi-tenant clouds and bare metal performance for critical workloads. However, having native performance and physical isolation compromises cloud manageability, since cloud operators do not install hypervisors on bare metal servers. They lose many essential manageability services provided by hypervisors, such as left migration, high availability, patching, and introspection-based security. In contrast, multi-tenant cloud providers compete to differentiate their offerings through rich hypervisor-level services. Can we have the benefits of both worlds? Our journey started from improving the performance of VM to match the bare metal performance. As you can see from the figure, the hypervisor sitting on the top of hardware manages 3 VMs. Typically, the hypervisor limits and emulates the device access by a virtual machine. Also, it handles the privilege instructions issued by the guest. This additional handling or emulation has a negative impact on high-performance devices or latency-sensitive applications. One idea is to partition the hardware and dedicate a subset of hardware to the guest, including CPU, memory, and I/O devices. The guest can directly access and control its dedicated hardware. This greatly improves the guest's performance. However, it levels up the difficulty for the cloud manageability, including left migration and introspection. And our goal was to bridge such a gap. We would like to have a hypervisor that helps its guests achieve the near-native performance without losing the capability of left migration and introspection. Directvisor provides both the direct device and local interrupt delivery. It allows the guest interacts with the CPU, memory, and device directly by the hardware-assisted virtualization. By directly, we mean no hypervisor intervention. With the support of Intel VTX and VTD, the guest operates on its own set of dedicated hardware without the hypervisor's help, while the hypervisor focuses on other tasks, including the left migration and security. Let's take a look at the Directvisor's architecture. Directvisor runs on its dedicated physical CPU 0. The guest agent works with the Directvisor and sets up the direct timer and IP delivery, and also left migration. The guest is able to configure the timer chips and handle the timer interrupts directly. The virtual processors send and handle the IPs among each other without any hypervisor's intervention. The guest access and controls the I/O devices directly, while the hardware takes care of the DMA and interrupt delivery. Moreover, the translation from the guest physical to physical address is also done by the hardware. Currently, Directvisor is implemented in Linux and based on QEMU KVM. It requires the Intel VTX and VTD support. It supports a Linux guest. The guests use the virtual functions of SRIOV devices such as network cards to run the I/O-intensive applications. Here is the overview of indirect and direct local interrupt delivery. As we can see, the difference between them is that the hypervisor is out of the way. By doing so, it improves the time interrupt and IP latency. Typically, the hypervisor keeps track of the guest timers and delivers the timer interrupts and API to the guest as virtual interrupts if the post-interrupt mechanism is supported. such deliveries is exodus. However, the issuing timers or IPI still requires the hypervisor's help. For the indirect time interrupt delivery, the guest attempts to program the timer chip and gets trapped into the hypervisor. The hypervisor examines the guest's timer requests and programs the timer chip accordingly. Then the control is transferred back to the guest. When the timer fires, the guest receives the physical timer interrupt. This triggers another VM exit. The hypervisor recognizes it's for the guest timer and injects the virtual timer interrupt into the guest. For the case of indirect IPI delivery, the guest attempts to program the IPI hardware or interrupt command register of LA PIC. It gets trapped into the hypervisor. The hypervisor validates the request and injects the virtual IPI to the target virtual processor. Directvisor allows the guest programs the timer chip and IPI hardware without its intervention. It helps the guest to use the post-interrupt mechanism to transform the physical interrupt delivery to virtual interrupt delivery. As a result, it saves the interrupt latency. The guest is directly in control of the timer and IPI hardware. One thing to note is this process is reversible. Directvisor can regain the control of guest dedicated hardware when necessary. Let's take a look at post-interrupt mechanism by Intel VTD. How does the assigned device directly deliver interrupts to the guest without triggering any VM exits? This requires that, first, the processor in the guest mode recognizes a special physical interrupt called the post-interrupt notification. When the post-interrupt notification arrives, the processor in the guest mode knows which guest interrupt handler should be invoked by looking at the post-interrupt request in the two data structure, post-interrupt request and virtual peak. The post-interrupt mechanism works as follows. VTD sets the bit for the assigned device interrupts in the post-interrupt requests. VTD delivers the post-interrupt notification and triggers the virtual interrupt delivery. The processor in the guest mode enters IDT. The processor in the guest mode invokes the proper interrupt handler for the assigned device. How does Directvisor helps the guest use the post-interrupt mechanism and achieve the direct timer interrupt delivery? Directvisor configures the following. It configures the timer chip to deliver post-interrupt notification instead of physical timer interrupt. It isolates the post-interrupt descriptor containing the post-interrupt request into a page. This page is shared with the guest. It disables the VM access due to the writes to the timer hardware, especially the timer initial counter register. When the timer value is written to the register, the timer starts to count. Directvisor initiates the first direct timer interrupt delivery by setting the timer interrupt bit in the post-interrupt request and programming the timer chip. When the timer fires, it delivers the post-interrupt notification and triggers the virtual interrupt delivery. The guest's timer interrupt handler is evoked. Then the handler first sets the timer interrupt bit in the post-interrupt request again, and then programs the timer chip for the next timer event. Since Directvisor disables the VM exit due to the writes to the timer register, programming the timer chip does not trigger any VM exits. Thus, the guest programs its timer events and handles the timer interrupts all without the Directvisor. Since both the network card and timer interrupt delivery use the post-interrupt mechanism, network interrupts can trigger spurious timer interrupts or early timer interrupts, which are filtered out by the guest agent. Similarly, Directvisor allows the virtual processors to send IPIs without its help. Directvisor configures the following. For the dedicated CPUs, it exposes the processor's IDs or LA PIC IDs to the guest. It disables the VM access due to the writes to the interrupt command register. Before the source virtual processor sends an IPI to the target virtual processor, the IPI handler sets the bit for the IPI in the posted interrupt request of a target virtual processor. Then the handler programs the interrupt command register of source LAPIC with the physical process ID of target virtual processor and post-interrupt notification. The source LAPIC delivers the post-interrupt notification to the target LAPIC, then triggers the virtual API delivery. Let's look at the performance improvements. We have several guest configurations here. First, Lena guest uses typical pathways for the timer and API events. DID guest uses the direct timer and API mechanism. DTID guests use only the direct timer interrupt mechanism. For the study of timer interrupt latency, DID and DTID guests should behave the same. The timer interrupt latency is the timing difference between the expected and actual wake-up time when the thread sets the timer. We ran the experiment with a sleep time of 200 microseconds for 10 million iterations. Unidirectional API latency is the difference between API sending and receiving times. To measure API latency, we register our own spatial API vector in the host or guest kernels. When the CPU received the spatial API, it recorded the timestamp. We send IPS between two CPUs with an interval of 200 microseconds for 10 million iterations. The cumulative distribution of both time interrupts and IPS are shown in the figure A and B. After removing Directvisor as the middleman, the median time interrupt latency is improved from 9.2 microseconds to 2.03 or 2.04 microseconds, which is about 0.5 microseconds behind the bare metal case. For the API latency, DID guess is about 1.1 microseconds behind the bare metal case. Next, Directvisor can live migrate the guest, having the direct access to its dedicated hardware while maintaining liveness comparable to traditional pre-copy migration for regular VMs. The guest agent configures the Ethernet bounding driver to bound the path-through and virtual network interface as one logical interface. The path-through interface is from the virtual function of SRLV network adapter. Under normal circumstances, the guest uses the path-through interface to perform network-intensive work. The general scheme of live migration is shown in the figure. A traditional hypervisor asks the guest agent to switch the guest network traffic to the virtual device. Hypervisor hop unplugs the path-through network interface and disables all direct hardware access for the guest. Hypervisor live migrates the guest via QEMU by the pre-copy live migration. Once the migration completes, the guest resumes on the destination server and continues using the virtual network interface. Hypervisor at the destination hot plugs a new path-through virtual function into the guest and instructs the guest agent to bound the new path-through network interface with the existing virtual interface. Lastly, the guest agent restores the network traffic back to the path-through interface. We compare the number of packet loss for 4 guest configurations. The guest receives 1 KB UDP packets at a rate of around 30K packets per second over the 40 gigabits per second link, while being migrated to the destination over the 1 gigabits per second link. 2 of the guest configurations are vhost only. The guest uses only a virtual network interface. Reactive switchover. Guests use a bounding driver to switch the network traffic between the path-through and virtual interface. As soon as the active path-through interface is hot unplugged, the bounding driver transfers the network traffic to the virtual interface. After the migration completes, the hypervisor hot plugs the new path-through interface, which triggers the switchover. And our goal is to match the liveness of a vhost-only configuration. It shows that packets are lost mainly during the migration preparation phase and the stop the copy phase. In contrast, the guests using the reactive switchover configuration experience the network disturbance during the hot plug and hot unplug events. Directvisor solves the problem of hot unplugging the active path-through interface by the managed switchover. The incoming traffic is proactively switched over at source before the hot unplugging operation and restores the traffic back to the pass-through interface after the hot plug operation. However, it does not eliminate the network downtime due to QEMU hot plug algorithm. The optimized switchover configuration overlaps part of hot plug operation at the destination while the source transfers the dirty memory. It effectively minimizes the network disturbance of hot plug operation. Directvisor summary and lessons. Directvisor enables near-native performance for the guest, while retaining the manageability and isolation benefits of traditional clouds. Directvisor goes beyond traditional pass-through I/O and enables VMs to directly control and receive hardware time interrupts and interprocessor interrupts, besides eliminating most VM access as shown in your VE paper. We realized that it is hard to eliminate the overhead of second-level address translation while using transparent huge pages or huge TLB file system can help to reduce such costs. And currently, we are working on the VM-based container technology, such as Kata Container, with the support of our Directvisor. Well, this is the end of my presentation. Thank you for your time and listening to my talk. Live long, prosper, and have a nice day.